Okay. Is the rate of change positive, negative, or constant? AKA, is it, you know, is it going up? Is it going down? Or is a curve going up? Is a curve going down? Or is it just staying exactly the same? What do you think? Anyone? Yep.
Negative.
The rate of change?
Oh, the rate of change is decreasing. Wait.
So, okay, so is the rate of change positive, negative, or zero? It is negative, right? It's negative. Here's my argument. Starting with a value of, starting at a point, let's say this is time or something, starting at 0, when I progress one value in the horizontal direction, my y value decreased. Another way I can represent it is I subtract, like the y value went down, I subtracted, right? If I move again 1x towards the right, my y value had to decrease. If I move 1 to the right, my y value had to decrease, and so on and so on. You get me? So yeah, I'm going down. So the answer is the rate of change is negative. Now here's the next question. Is the rate of change changing? Yes or no? Yes. Right? How is it changing? Is the rate of change increasing or is the rate of change decreasing? And this is where you have to think carefully. And I encourage you to be wrong. Maddie, why do you say it's decreasing? Okay, stop right there. Does everyone agree? The dotted line that I drew for the first block and the dotted line that I tried to do for the second and the dotted line for the third, dotted line for the fourth, they are getting smaller and smaller. Yes? Correct. Now, if we talk about it with numerical values, is the number itself getting smaller? That's the, but think carefully, okay? And this is what spills over into applied mathematics and applied sciences. Let's, hypothetically, let's pretend this subtraction is what? 1, 2, 3, 3.5. I went down by 3.5 in the first block. What about this one? How much did I go down by approximately? 1 box, 2 box, and a bit. The second step, I went down by negative 2.5. What about the third box? 1 box and a bit. Here, I went down by approximately negative 1.5. What about the next one? About 1. What about this one? About half. So here's the million-dollar question. Is negative 3.5 larger than negative 2.5 or no? Absolute value-wise, sure. But Ethan?
I mean,
yeah. Why? Because of the negative. A negative 3.5 is further away from the 0 than negative 2.5. So technically, negative 3.5 is smaller. In this situation, what is the correct answer? The rate of change is actually increasing. Right? Because negative 2.5, how do I get to here from negative 3.5? I had to add by 1. Negative 3.5 plus 1 is this. I increased it. Plus 1 is this. I increased it. Plus 0.5 is this. Plus 0.5. Here's another way you can think about it. People who are like, what? You think about it this way. If I continue this trend, at a certain point, if I kept on doing this, I might reverse it, won't I? What do you think? If I kept this up, is it possible, maybe, that I would reverse the trend, it would go back up? I mean, try to use your imagination, maybe, right? I don't know, but if you think about it that way, if you keep up this trend, I think it's a little easier to understand. It was like, oh yeah, it is going up after all, right? It used to be really, really, really in the negative, but it's slowing down because I'm trying to bring it back up. Here's another example for those of you who are more money inclined. Let's pretend this is the amount of money in your bank account. And this is every month. Every month, you're losing money in your bank account. But the amount of money in your bank account, before hitting zero, we're slowing down that minus, the deficit. We're trying to save money, hopefully it'll go back up. Does that make more sense? I'm not quite sure. I'm trying to convey it to you in different scenarios, but when we talk about rate of change, this particular question, it's increasing. And so even if last class's lesson seemed easy, you have to consider every scenario carefully. Don't rush it. Don't rush it. Okay? Any questions before I move on to today's lesson? If you do have questions, by all means, come and see me. I want to get started on lesson 3, linear versus nonlinear. So last class, 5.2, we looked at a whole bunch of graphs. Some were straight lines, some were curves, and we talked about the rate of change. Both examples had some kind of rate of change. And then we talked about whether it was increasing more and more and more and more and more, or if it was staying constant. Today's lesson is simply put, is it constant or is it not constant? Is the rate of change put like not changing and as is, or is it constantly changing as we move on? That's it. Once we establish that, I'm going to give you some shortcuts so that you can pinpoint what the movement is like without doing any math. Once again, it's to look at something and be like, oh yeah, I understand that. Okay? Let's try to look at this without too many numbers, and hopefully you'll feel more confident when you start using numbers. Here we go. Linear versus nonlinear. The key idea is this: a linear relationship between two variables, you see it as a straight line. I don't think that's something that you'll be confused with, right? The word linear, the root behind that is align, L-I-N-E. And so on a graph, you'll see it as a straight line. If you have a nonlinear relationship, not a line, it's not going to be a straight line. Is everyone okay with that? Yeah. Okay. But obviously, the lesson's not as simple as that. We're going to look at different ways we can identify it with numbers. I know all of you can tell me if it's a straight line or not. I do. But can you tell me that even if I give you numbers and not a picture? See if we can get that. Nate, question?
For B, there are two-ish straight lines.
Yes.
So would that be considered straight because it's straight, or not straight because
So let's talk about it, okay? That's actually, it's a little bit of an asterisk, but I'll show you in just a second. Determine whether each of the following graphs represent a linear or non-linear relation. This one. Yes or no? Thank you. Check. That's it. I think that's self-explanatory. I'm not going to go any further. B. Someone else? All right, it's not supposed to be a trick question. Someone else? Oh, Ethan? Yes. Right up. If you're not sure, another way you can check is literally do the staircase. Is the staircase consistent? Yeah. Is the staircase here consistent? No. That's one way you can check, okay? Next one, linear and nonlinear. Someone else. Thank you. Brian M. Yeah. So now we come to this. Who says linear? Take a guess. Who says nonlinear? Okay, you're both right and wrong. There's a right aspect to it and there's a wrong aspect to it. You are correct in saying, oh, that's a straight line. That's a straight line. They're both straight lines. Why can't it be linear? Technically, you're right. But in the world of mathematics, being very, I'm going to say it, very anal with detail, a straight line, a linear relationship, when it is actually a non-changing straight line. In mathematics, this is actually called an absolute value, where the y value is going to be something funky like this. The x is affected by something. It does satisfy some conditions of a linear relationship, a linear equation, right? But it doesn't satisfy all of them. And I'll talk about that detail after. So case in point, if you want to take something home, the start is linear. You can think about that as non-bending line. Okay, I put a little asterisk there so you don't get confused. Which brings me to the next one. That is a perfectly vertical line. Linear or nonlinear? I encourage you to be wrong. Who says linear? Okay, who says not? Okay, so in this particular case, under the mathematical definitions, you would say it's linear, but with another asterisk. It's special. And the question I want to ask you for this one is, if it's linear, how would you describe the rate of change or the trend? Is it increasing? Well, it's going up. Is it decreasing? What's going down? Sort of, but we're not even moving left and right. At a single location, it's going up infinitely and it's going down infinitely. Blows your mind, huh? Sorry, I didn't mean to hurt your brain, right? But like at a single point, it's infinitely going up and it's infinitely going down. Technically, we would call this linear because the line is not bending. However, the trend or the rate of change is undefined. Another way we could say it, the rate of change is actually infinite. I'll talk about what's the more correct definition much later, or you might get a chance to see it when you dabble into it in grade 11 or 12. But for the moment, these things are going to be a little bit special. You won't have to worry too much of that anytime soon. Yes? D is, oh, how did I draw linear here? Thanks for catching that. It is nonlinear. Okay? Let's move on. So what are we more focused on? We're clearly going to focus more on the linear aspect of things. So my question again is, how do you know if something is linear or not without a graph? How do you know something is non-linear or not without a graph? I'm going to ask you to do some counting, please. Ready? Example. Here's a pattern. Do you see the pattern? Right? Here's a square. I'm adding a square on top and a square to the right. And it essentially creates a staircase as I get larger and larger and larger. The next staircase will probably look like this. Something like that. Okay? Complete the table of values below for each frame with the perimeter. So let's count. Frame 1. 1, 2, 3, 4. Perimeter is 4 units. Don't worry whether it's centimeters or meters. I don't care. Frame 2. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. What about frame 3? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12. And lastly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. See a pattern? Every time the frame increased, what happened? Plus 4, plus 4, plus 4. So even without drawing the next frame, what do you think the number will be? Hence, the beauty of relationships. What if I told you then, those of you who are more mathematically inclined, what would be my perimeter if my frame was 20? Whoa, I'm not going to ask you to do that, but if you had some time, do you think you could figure it out? That's what a relationship is. That's a relationship, right? Let's continue on. So yes, this step 2, most likely adding by 4. What about area? As you know, area is the space covered by the shape. So frame 1, I have 1 square. Frame 2, I have 3 squares. Frame 3, I have 1, 2, 3, 4, 5, 6 squares. And frame 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. And I don't want to draw frame 5. But is there a pattern? Is there a relationship? Well, let's take a look. How much did I increase by? 2. How much did I increase by? 3. How much did I increase by? 4. So it makes sense that the next number should be is my rate of change positive? Yes. Is my rate of change changing? Yes. Is my rate of change positive? Yes. Is my rate of change changing? This is the difference. And that will also create a completely different image on the graph. Let's do it. Would you take about a minute to graph this for me? Perimeter, frame number. The first one's easy. 1, 4. 2, 8. 3, 12. 20. And also, if you think about it, if you had 0 frames, I would have 0 perimeter. So you can technically say that also fits. There. Yes. No, while that is up there, try that area. Oh. So the next one, let's see, this one you might have to do a little bit in between lines. So frame 1, area is 1. So that's actually half of a box. Frame 2 is a 3, so it's 1.5 of a box. Frame 3 is 6, so that's between 8 and 4. Frame 4 is a 10, between 8 and 12. Frame 5 is 15, so it is just underneath the 16. And of course, if I had 0 frames, I would have 0 area. That makes sense? Well, take a look. Let's see if I could do this in one shot. Huh. Now, ain't that something? Again, if I gave you this graph or if I gave you this graph, I think you'd be able to tell me if something is linear or not. Yes? But what if I gave you that chart? Or what if I gave you that chart? In other words, what if I only gave you numbers? Can you also tell? And if so, how? Right? And thank you for saying differences. We are going to do some kind of subtraction. All right. So if you need a chance to copy that down, copy that down. I am going to answer so that you have the next questions on the bottom so that you have something underneath. And then we'll try some questions together. Okay. This thing called first differences. Here we go. The bottom section says, describe the relationship between frame number and the perimeter. Is it linear or is it nonlinear? I'm going to say, let's do this. When frame number increases by 1, perimeter increases by 4. Every single time. Linear. And just because I think it will be good for some people to see this, I'm going to add a little bit extra here. Rate of change. In this case, if you remember the definition I gave you last class, I said rate of change is basically how much y changes over how much x changes. And of course, in this case, x is always changing by 1, right? So the rate of change is going to be a positive of 4 in your perimeter for every 1 frame. So it's basically 4 units for my perimeter over 1 frame. Does that ring a bell from all the way back in February? The rate of change is 4 units per frame. It's a unit rate. It's a fraction. It's a proportion. So all the stuff we've been doing since way back in the beginning of February, we're going to bring it all together. Yes?
What's that between the rate of change and the slope?
Nothing. That's exactly what it is. But rate of change, it's in the context of a story, like frames and area and perimeter. Slope is the most basic mathematical definition. Here's a number that's going up and up and up and up, or down, 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 down. It looks like a hill, let's call it a slope. Like, that's it. But they're one and the same. Second one, I'm gonna do this in text. When frame increases by 1, area increases by 1 more than the previous change. Oops. So in other words, the rate of change is not constant, it's non-linear. Right? How many people here have already established in their heads that the way that you can check whether it's a straight line or not is just looking at the y values and subtracting, checking for the difference? Has everyone already established that in their heads? Yeah, does it make sense? Because I've been drawing the lines up and down every single time we did it in a graph. That's today's lesson. But the mathematical term behind what we were doing until now and what you might be doing as intuitively is something called first differences. The first time you're doing a difference. So, this is what you're looking for. If the first difference, so one way to determine whether something is linear or not when you're given numbers is to look at the first set of subtractions, first differences. If the first differences are constant, the relation is linear. If the first differences are, well, not constant, the relation is nonlinear. I think it sort of makes sense. So let's do it. One thing you want to make sure you're doing correctly. Everyone here pay attention. Nate, you with me? Andy, you with me? Andy? 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 Hello? Someone want to like just gently poke her? Hi. Trying to get your attention for a little bit here. This is very important. I need you to put that down for like 30 seconds. Okay? When you're doing first difference, it's always the lower number subtracted by the top number. If you don't do this, things in grade 10, things in grade 11, a lot of other things you will confuse yourself with. So always remember, when you're doing first difference, lower number minus the upper, or the second number minus the first number, the third minus the second, so on and so forth. I just wanted to make sure everyone got that. So 8 minus 4, 4. Lower number minus the upper number. 12 minus 8, that's a 4. 16 minus 12, that's a 4. If you do it in reverse, you'll actually end up getting a negative version of that, and you'll be like, oh, those numbers aren't the same. But in fact, you have to be consistent. Do you see how every first difference is the same? Linear. This relationship is linear. Please do that for the second one. I'll give you like 30 seconds. I think you can do it. Three minus 1, 2. 6 minus 3, 3. 10 minus 6, 4. You see that the first differences are not constant. If you see that, you know it's increasing more and more and more, or it's decreasing more and more and more. This relationship is nonlinear. There's no way. All right. Can we handle one more? Can we handle one more? If I give you a graph, can you tell me if it's linear or not? If I give you a table of values, can you figure out if it's linear or not? Use words. Use words. But what if I gave you an equation? Again, now we're moving into the math portion. When you're ready, turn the page. What if I give you an equation? How do you know? Here's what you could do. Or actually, someone have a creative idea. The only way you know how to figure it out right now is if I give you a graph or I give you a table. Any ideas how you can use that if I give you an equation? Good question. You might be a little shy, so here's what you could do. Number one. Oh, yeah.
I really no idea what I'm guessing, because there's y and x in there, we're indicating that that's so y.
Yeah, so let's say your x is 1. Substitute in the 1, solve it, and if x is a 1 on your Cartesian, your partner y is, what, 2 times 1 is 2 minus 3, negative 1. So if x is a 1, my y is a negative 1. You can create a table with this equation and then do first differences. So let me show you the annoying way, all right? So that you can appreciate what I'm going to tell you. So I'm going to create a table of values. You don't have to do this, please. Just follow along. If x is a 0, 0 times 2 is a 0, minus 3 is a negative 3. If x is a 1, 2 times 1 is a 2, minus 3 is a negative 1. If x is a 2, 2 times 2 is a 4, minus 3 is a 1. If x is a 3, 3 times 2 is 6, minus 3 is a 3, and then you can do first differences. What do you think? Well, you could do that, or you can try this shortcut. Ready? If we're dealing with a linear equation, the largest exponent on the x, aka the largest degree, is a 1. Period. End of lesson. The easiest way to identify if an equation is going to give you a straight line or not is to look at your x terms. So look at A, look at B, look at C, look at D, look at the x terms, and see if the exponent on the x is a 1. If it's a 2, 3, 4, or anything more than 1, it's not going to be a straight line. I can guarantee that. This is what I'd like you to write. The degree of a linear equation must always be 1. This means that the greatest exponent you should see in the x term is 1. So take a look. Here, I'm going to be extra annoying with you, okay? So bear with me. Here, that is x to the power of 1. And here, you can say that x is actually to the power of 0. It doesn't exist. So what's the largest exponent you see? 1, right? It's right here. So it's the largest degree. So the greatest degree equals 1. This is going to be linear. It's going to give you a straight line. How about the next one? Here I see x equals 2. Here I see x equals 1. Here I see x equals 0. What's the greatest degree? 2. It will not be linear. All right, nonlinear. Now I could guarantee that if you decided to do a t-table, right, a t-chart, plug in a 0, plug in a 1, plug in a 2, plug in a 3, and get all these values and then subtract it, you will see that these first differences are not going to be the same. I'm not saying you can't do it that way, but this is the relationship that we see. Every time it's an x to the power of 1, it's always giving us a straight line. If it's not, it will never. Let's do D. What's the largest exponent you see? So the greatest degree, the biggest degree that we see, so the largest, is a 2. So it's nonlinear. How about E? Someone else. What's the largest degree that you see? So, Ellie? Yeah, that's it. We see that to the power of 1, and that's all we need to focus on. Don't be distracted by the coefficient. Just because it's a decimal doesn't change anything. It's a linear. Which brings us to the last one. Heck is that? Take a guess. It would be. And let me explain. Up until this point, you've done algebra for me, so I know I can say this. X minus 2 to the power of 2 is like saying x minus 2 times x minus 2, correct? So far, so good? And when you have two brackets next to each other, what did you learn to do? Distributive property. So sooner or later, x will get a chance to multiply with x. So I don't know what the entire thing is, but I do know this polynomial starts with x squared before I finish it off. The largest exponent for that one is 2. Okay, so greatest degree equals 2. So this is nonlinear. So there are some sneaky questions that I can ask like that, but as you can see, this kind of skill you've done before. It's only a matter of creative thinking and being like, how can I turn this into a situation that I remember or that I'm familiar with? You realize it is to the power of 2. Okay, let's finish off our note and we can sort of relax while you try some homework questions for me. Conclusion. Conclusion. I know that a relation is linear if the graph is linear means a graph is a straight line. Right? So no curves. How can you tell if the only thing I give you is a table of values? I know it's a linear relation if the first differences are equal. I'm going to say the word constant. So same value, they're equal. If it's linear, if I give you an equation, the exponent or the degree must be. Okay, so e.g. it could be x plus 3 or 5x minus 11, anything like that. If it's nonlinear, someone else want to give it a shot? Patrick, you with me? Nonlinear. How do you know if a graph is nonlinear? Not a straight line. Okay, so curve. First difference is? Someone else? Warren, you with me? Yeah. Not equal. They are not constant, right? Okay. Or even if one is different, it still doesn't work, right? The degree of the equation then is more than 1. Well, yeah, it can actually go both ways. Not 1. It could be more than 1. It could even be less than 1, actually. It could be like an x to the power of -1, but that is not linear. Okay, so some examples, you could say, 2x squared plus 5. That's the exponent of 2. How about like, or x to the power of a -1 even, right? That's not linear. Okay, a bunch of different things. In any case, that's the lesson. I know that there's independent practice. There's 1, 2, 3, 4 questions. We do have about 15 minutes to ourselves. You can sort of relax. But sometime between now and Monday, I would hope that you at least try one or two from each question. So 1 AC, number 2 ACE, number 3 all of it, number 4 all of it. Any questions? All right, then we'll stop here.